Imagine you're at an arcade and you're playing one of those games where you have a claw and you're trying to move the claw over a prize. I don't know, it's like a Furby or something. Instead of a joystick on this machine that you're playing, you've got two buttons. So on one hand, you've got button A, and button A will move the claw. So in this case, it's 94 units, we'll say millimeters horizontally, and 34 units up. And it costs 3 tokens to press button A. Similarly, you've got button B, which does the same thing, but moves it a different amount, both horizontally and vertically. But this button only costs 1 token to press. And you know the position, you know like the X and Y position of the prize. So your goal is to figure out, can I get the claw directly over the prize? Is that even possible? And if so, I want to do that in the cheapest way possible between pressing buttons A and B. So I could look at this problem and I could say, well, I know there's some series of button presses, between A and B that will get me there. But the problem is that sequence of button presses is really hard to not only figure out, but just to keep track of. And so I looked at this problem during this year's Advent of Code, and I was like, oh, I've seen problems like this before. I know how to solve this. I'll use a tree. I'll use a state space tree, and I'll solve this problem. So how that could work is, I can imagine drawing a tree here. So on one hand, I could press button B, and on the other hand, I could press button A. Now, if I press button A, I know that will cost 3 tokens, and I know that will get me to 94 and 34. On the other hand, if I were to press button B, well, that would cost me 1 token, and it would be 2267 as my position. And then from here, it just is recursive. So again, I could imagine pressing B, and I could imagine pressing A. If I did B and then A, I could see my token costs go up to 4 because 3 plus 1 is 4. And then my new horizontal position is 116, and then vertically I'm at 101. And so you can see this keeps going, and it just forms basically a binary tree. I would just repeat this over and over for basically a lot of different combinations. And it's sort of like the tree gives me like different versions of reality. It's like a way to see different versions of reality. Like I can see if I chose A, and then if I chose B, and etc. So that helps me mentally picture the problem a lot better. Like I can write it out by hand. And more importantly, it's like not too hard to write a computer program that follows this pattern. So that's what I did, and it worked, and I actually felt really smart. But then the problem changed. The problem got a lot bigger. So now the goal was no longer, at, what was it, 8,400, 5,400. Now it was literally 10 trillion, we'll say millimeters, 10 trillion more than that. So the problem got so much bigger. So at first I thought, no problem. I'll use my clever tree idea here. I'll run my program and I'll get the answer. So I executed my program, but it never stopped running. So what's going on? Like, how big is this tree getting? To figure that out, let's try and simplify things a bit. So let's take out the vertical position. Let's take out the tokens. Let's just pretend like we have to move horizontally from some point to another point. We know the prize was at 8,400 millimeters. We start at 0. So let's imagine I only press button A. So if I do that, that's like jumping towards this goal 94 units at a time, which is about 89 presses. On the other hand, I could imagine pressing only button B to get to my goal, and that would be moving 22 every time. And that comes out to be about 381 presses. So that's B. So what do these numbers tell us? Well, the 89 is kind of like a lower bound in a way, because if you can imagine our tree, it's going to be sort of shaped like a triangle. And on this side is where we're only pressing button B as we move towards the bottom. And we said that was 381. 381 branches here, because every time I press a button, that's like a branch in the tree. And then similarly, this side represents that I press button A every single time. And we said that was 89 presses. And so, this side is obviously quite a bit longer. We can imagine that we might end up with a tree or a triangle that is shaped something like that. We know the answer isn't actually going to be all B presses or all A presses. But we know our answer is probably somewhere in the middle here. It's going to be a combination of both. And again, it's not like my program is actually building up a tree like data structure. It's more like this is the pattern that the algorithm follows to as it goes through all the different possible states. If we say a step is like a branch in the tree, how many nodes are in this tree? Well, there's a formula for that. So 2 to the power h, I think it's plus 1, minus 1. This tells you how many nodes are in this whole tree. And since 381 is kind of our upper bound, so like it gets bigger on this side, we could do a really rough estimate and say that there are 2 to the power of 381 plus 1 minus 1. So I don't know what number that is, but that's a really big number, obviously. And I should say this is like a really big overestimation. Because in reality, we can make our algorithm make it so it doesn't have to go through all the different nodes in the tree. But this is just a really rough estimate. And this is a really big number, 2 to the 381st plus 1 power. And this is before the problem grew to like by a trillion. So this is with the small goal. So you can see it's just too many steps for the computer to do realistically. This is going to take hours or days. You know, it's going to take a long time. So let's look at the problem from another perspective. So you could say that there's some amount of A presses plus some amount of B presses that gets me to the goal, which is 8,494 comes from the A button, and 22 comes from the B button presses. So some amount of both of those should get me to 8,400 if it's possible. Similarly, I know there's some amount of A presses plus some amount of B presses that get me to 5,400, which is the vertical position of the goal. When I press A, I know that that moves me 34 vertical millimeters. And if I press button B, that moves me 67. Maybe you already see how this is useful, but math does not really, it's never really come super easily to me. So I'm going to try to explain this in like the clearest way possible that I can for those that are like me who may not understand immediately. What we have here is called a system of equations, and so I've got 2 equations and I've got 2 unknown variables. The trickiest part, in my opinion, is like just trying to figure out where the numbers go. If you can get that, it's usually pretty easy from there. And so I've made it so the first equation corresponds with the horizontal position that I need to move, and I've made it so the second equation corresponds to the vertical position that I need to move. And this leads me to the goal that I hope to find. So to solve a system of equation, there's actually a lot of different ways you can do it. There's a few different ways. For example, you could use substitution, and I'm not going to go through that here in the video. But basically, you first solve for one of the variables. So in this case, I would first get A, on one side of the equation, and then I would plug that into the second equation, and I would use that to get B, and then I would turn around, I would have a value for B at that point, and I would turn around and put that value back into the first equation to finally get A's value. And so once we solve the system of equations, we'll be left with a value for A and B, which A equals 80, B equals 40. So I need 80 presses on button A to get to the prize, and I need 40 presses of button B to get to the prize. And I can tell in this case that it's a legitimate solution because they're whole numbers. They don't have a remainder. If I were to get like 80 and a half, I would know that that's not actually a valid solution because it doesn't make sense in this case. You can't have a half of a press of a button. Finally, to get the answer of how much it costs, I can just plug these values into the formula, the token formula, you would say. And you might be thinking, what is the token formula? Well, if you remember, we said that a press of button A was 3 tokens and a press of button B was 1 token. So I'm going to say that T, which is the token cost, equals some number of A times 3 plus some number of B presses. And we know those answers, so I can plug that in and get T equals 80 times 3 plus 40, which equals 280. So that's how many tokens it'll cost me to get the claw over the prize. One last thing is that I actually realized it's kind of hard to do algebra like in a computer program, at least in the same way that I'm used to doing it like on paper. But after some Googling, I realized you can actually use matrices to do that. And that sounded scary to me at first because, you know, I've never really done that, to be honest. But it turned out to be actually kind of straightforward. Anyway, I just wanted to say that I really enjoyed working on this problem. I found it super interesting and I actually learned a lot. Like I said, math has never really come easy to me, and problems like this give me a really great appreciation for like knowing how to do math. It makes it like really applicable and fun, and it helps me see the value of this really cool like tool that we have to solve problems and like look at the world around us. And I thought I was being clever with like my tree approach that goes through the problem and basically brute forces it. And once the problem got bigger, it just totally like was not working. Like I tried to optimize it and optimize it. It just was not working. I could not get it to solve the problem. But then you've got this mathematical approach that just comes in and solves the problem just so simply, so efficiently, so elegantly. It's really cool to see. I guess it just goes to show that math helps.